Hello, so this is a revision video for NCERT Class 11 Chemistry 5.1 Thermodynamic Terms. This is a revision video, so it only covers the essential information you need to know. For deeper explanations and for full video lessons, please check the links in the description below and visit chemistrystudent.com. Thermodynamics is the study of energy changes during physical and chemical processes. It is really important to understand what we are referring to when we consider energy changes. The system is the specific part of the universe under thermodynamic investigation. The surroundings are everything external to the system that can exchange energy or matter with it. A boundary is the real or imaginary surface separating the system from its surroundings. The universe is a system and its surroundings combined. Thermodynamic systems are classified based on the exchange of matter and energy. An open system is one where heat and matter can flow in or out of the system. A closed system is where heat can flow in or out, but matter can't. And an isolated system is where no heat or matter can flow in or out of the system. The state of a thermodynamic system is defined by certain measurable properties, known as state variables or state functions: pressure, volume, temperature, and composition. A change in state is described by how these variables change. When a system undergoes a change, energy transfer may occur in two forms: work and heat. Work is the energy transferred when an object is moved by a force. It's commonly seen in expansion or compression of gases. Work is a path-dependent quantity. It depends on how the process is carried out. Heat is the energy transferred due to temperature difference between system and surroundings. It is also path-dependent, and like work, heat alters the internal energy of the system. Energy can enter or leave a system via both heat and work. They aren't properties of a system, but rather of a process. When either heat or work is supplied to a system, its internal energy changes. This is very important to remember. In thermodynamics, we define a system's total energy as its internal energy, U. This includes all forms of energy present within the system, for example, chemical, electrical, and mechanical. The internal energy may change if heat is transferred into or out of the system, and if work is done on or by the system, or if matter enters or leaves the system. To understand how work affects internal energy, consider an adiabatic system. An adiabatic process is one where no heat is exchanged between the systems and the surroundings, so Q equals 0. An initial state of A is given by temperature TA and internal energy UA. The final state will be given as temperature TB and internal energy UB. This means the change in internal energy will be delta U equals UB minus UA. Consider two possible examples. Imagine you have a beaker of water and you add 1 kilojoule of energy in the form of mechanical energy. The temperature rises, so TB is greater than TA, showing an internal energy increase due to work input. Now let's imagine the same size beaker and same quantity of water where we also add 1 kilojoule of energy from an electric heater. The same temperature rise will also happen. TB will be greater than TA. What this shows us is that the change in internal energy is always the same regardless of the type of work done. The path doesn't matter. This experiment, originally by J.P. Joule, showed that regardless of the method, if the same amount of work is done, a system undergoes the same change in internal energy. Hence, internal energy depends only on the state, not the path. It is a state function. Now let us consider a system with thermally conducting walls, for example a copper container in contact with a heat reservoir, like a large body of water. If water in the system is at temperature TA and the reservoir is at TB, heat flows from the reservoir to the system, if TB is greater than TA. This thermal energy transfer is termed heat. If no work is done, the entire energy change is due to heat, meaning delta U equals Q. This is a non-adiabatic process. Now, in most real situations, both heat and work affect the internal energy, and based upon the two examples we've just looked at, this gives us an equation of delta U equals Q plus W, and this is referred to as the first law of thermodynamics. Now, although Q and W depend on the path, their sum depends only on the state, reaffirming that internal energy is a state function. And this also shows us that if a system is isolated, so there's no heat or work transfer, then Q is always 0, W is always 0, which means delta U is always 0. Now, it's really important to note here that internal energy isn't directly measurable in absolute terms. Only changes in internal energy are physically meaningful, unlike properties like volume, which can be directly measured.